In our digital world, we're constantly fighting this invisible battle. How do we prove that our data is exactly the same as it was yesterday or a year ago? How do we really know it hasn't been changed? Well, the answer isn't just some password or a lock and key. It's this incredibly elegant mathematical idea that, as it turns out, is the very backbone of technologies like blockchain.
So let's think about it this way. If you've ever worked with a database, you know what a primary key is, right? It's that unique ID for a row of data. But what if that key could do more? What if the key itself could guarantee that the data it points to has never, ever been altered?
That is the perfect question, because the answer is something called a hash function. And honestly, the best way to think about it is as a unique digital fingerprint. It doesn't matter what the data is, a picture, a contract, a single word, a hash function can generate a one-of-a-kind fingerprint just for it.
And here's where the magic really happens. This process actually condenses the data. I mean, you could feed it the entire text of a massive book like War and Peace, or just the word hello, and the digital fingerprint that pops out, we call that the hash, it's always going to be the exact same fixed length. It's just an unbelievably efficient way to represent a huge amount of information. Now, it is absolutely crucial to understand that this is not encryption. See, encryption is a two-way street. You lock your data with a key, and someone with the right key can unlock it and see the original info. Hashing, that's a one-way street. Once you create that fingerprint, there's no going back. You can't reverse engineer the original data from the hash. It is fundamentally a one-way trip.
Okay, so a one-way digital fingerprint. I get it. But how does the computer actually make that fingerprint? What's really going on inside the engine? Well, that's a great question. So let's pop the hood and look at the specific algorithm that Bitcoin uses. It's called SHA-256. The cool thing is, the concept is actually pretty straightforward. You start with whatever data you want, that's your input. You run it through the mathematical gears of the SHA-256 algorithm, and what comes out the other side is always a unique 256-bit string of characters. Always. No exceptions. Just take a look at this example here. We've got the simple sentence, "The quick brown fox jumps over the lazy dog." When you run that through SHA-256, it produces that long, complicated-looking string. That's its unique digital fingerprint. And remember, if that input was just one letter or 1,000 pages long, the output hash would still be that exact same length. So I can see the process. But what makes it so special? What makes it cryptographic? Where does the security come from? It all comes down to a few very strict rules these functions have to play by. First off, the function has to be deterministic. All that means is that the same input will always produce the exact same output. You could feed it the same file a million times, and you'll get the identical hash back a million times. If it wasn't consistent like that, you could never actually use it to verify anything. Second, it has to be fast. I mean, think about it. A system like a blockchain is processing a massive number of transactions all the time. Generating each one of those digital fingerprints has to be almost instant. If it wasn't, the whole network would just grind to a halt. And third, and this is a big one, it needs something called pre-image resistance. This takes us right back to that one-way street idea. Basically, if I give you a hash, it has to be practically impossible to work backward and figure out what the original data was. Now, notice I said practically impossible. You could technically try to guess, just hashing random stuff until you find a match. But with a 256-bit hash, the number of possibilities is so ridiculously huge, it would take all the computers on Earth billions of years to get it right. So, yeah, practically impossible. Okay, so deterministic, fast, and one way. I've got it. So how do those rules actually translate into security in the real world for something like a blockchain? This is where it gets really cool. It's all because of something called the avalanche effect. Look at this. We hash our sentence and we get that specific fingerprint. Now watch, we're going to make one tiny, tiny change. Just change the capital T to a lowercase t. Now, logically, you'd think maybe the hash would change just a little bit, right? But nope. Look at it. The new hash is completely different. It's totally unrecognizable. Even the smallest possible tweak to the input causes this massive, unpredictable avalanche in the output. And that is how you make any tampering instantly obvious. And finally, there's collision resistance. This sounds complicated, but it just means it's basically impossible to find two different inputs that accidentally create the same hash. So every unique piece of data gets its own unique digital fingerprint. You can't just create a fake contract and hope it happens to have the same fingerprint as the real one. It's not going to happen. This is what makes the whole system trustworthy.
Okay, so let's put this all together now. If you had to summarize it, why is this one single mathematical idea so completely fundamental to the entire concept of blockchain?
Absolutely. Hashing is the literal bedrock. It guarantees data integrity. That's the avalanche effect we just saw, making any change stick out like a sore thumb. It creates the chain of trust because you can link blocks of data together with these fingerprints. It makes the records tamper-proof because working backward from a hash is, well, infeasible. And it gives us incredible efficiency by letting us represent huge amounts of data in a small fixed-size hash. Put all that together and you get a secure, unchangeable ledger without needing some central bank or company to guard it.
So, to put it as simply as possible, hashes are the bedrock of immutability. They turn regular data into verifiable, unchangeable digital artifacts. We really hope this explainer helped make the idea of hashing click for you. If you found it helpful, hey, do us a favor and like, share, and subscribe. We've got more deep dives like this coming up. But it really does leave you with a fascinating thought, doesn't it? This one simple mathematical function is powerful enough to secure a global, decentralized financial ledger. So the real question is, what other systems in our world could it transform next? Voting? Supply chains? Something to think about.